section, we'll be talking about the components required to build a power electronic system. And we'll also be dealing with some basic know-how of power and energy signals, and then the use of Fourier series in harmonic analysis. So before studying the semiconductor switches, which are called active elements, we will be studying these passive elements. So first, passive elements in this section, and how to do power analysis and Fourier analysis when we use these passive elements in a power electronic circuits. So three passive elements we already know of: resistance, inductance, and capacitance. Resistance is normally not used in power electronics because they consume power and dissipate it, and without doing any useful work. So that's why resistance is normally not used in power electronics. So we can strike off this passive element for use. Inductance and capacitance, they are the major components, passive components for power electronic circuits. And just by configuring this inductance and capacitance values and orientation, we can change the topology, and then we can change the parameters, the required parameters in terms of efficiency, output power, output current, and so on. And then we also make use of active elements in power electronics, which also play an important role in improving the required parameters such as efficiency, load, current, and load voltage or load power. So we need to design efficient control system or control algorithms for controlling these switches, which are normally semiconductor devices such as power diodes, thyristors, BJTs, MOSFETs, IGBTs, and so on. So in this section, we'll only be dealing with the passive elements, followed by active elements in the next section. So now, what is instantaneous power? We already know that instantaneous power in any component computed by using the voltage across it and the current in it. So this instantaneous power denoted by P, argument T means a function of time, power a function of time, equal to voltage, again function of time, multiplied by current, again a function of time. So in power electronics, this instantaneous power is actually calculated so that come to know about the power rating of a power electronic system. So in this case, we know that if voltage is in volts, current is in amperes, this power, instantaneous power, is in terms of watts. And then what is energy? So energy is normally, in this case, if we're talking about, so this is power, which is a function of time, multiplied by the time, and denoted by joules, means the units are joules. We already know about this. So this power flowing in a circuit from time instant t1 to the time instant t2, multiplied that particular time, multiplied by that particular time, we get energy in that particular circuit. So we'll do examples of this so that you can understand it better. Now, average power. This also you might have done in your basic electrical and basic electronics course, but this is just a revision that if somebody has missed out on this thing, on instantaneous power or average power or RMS, So they can revise it. So periodic voltage, and we already have seen that in power electronics, the signals are mostly periodic in nature. This sinusoidal signal is periodic in nature and keeps on repeating forever. So periodic voltage and current functions produce a periodic instantaneous power that we can easily relate out. So average power is the time average of this instantaneous power over, for example, one time period of a sinusoidal waveform or any periodic signal. So average power, so how mathematically, how we can do it? So this instantaneous power, which is a function of time, this instantaneous power, function of time, starting from this time instant t0 to this time instant t0 plus t can be one complete cycle. So starting from some time instant to the time instant plus complete cycle. And for that complete cycle, how much power has flown? Which is, you can say, broken down into small deltas of a time, which is dt. So at every instant of time, starting from here to here, so for every instant of time, that means limit tending to 0. So very small instants. So all instants we take, and at every instant we measure this instantaneous power, and then integrate it. Integrate means sum it. So sum all the power values at that particular instant dt, starting from here to here, and then taking an average by dividing it by the total time period, which is one cycle, for example. So dividing by the time period taken for one complete cycle to take place. So one complete cycle of a sinusoidal is 0 to 2 pi. So 360 degrees. So in time period, let's say it takes from 0 to 2 pi takes about 1 second. So time can be 1 second. If it takes 10 seconds, so we can say 10 seconds over here. So starting from, let's say, 0 to 10 seconds. And every time instant, let's say dt is 1 second, if t is 10 seconds. So at every 1 second, we take a value of instantaneous power, integrate it, and then divide it by 10. We get an average power. Because instantaneous power. So now this average power is known by some other names also, like real power or active power. So active power means it plays an active role in power consumption. Another type of power we will see when we do inductance and capacitance, they are called reactive powers. They don't do useful work. So that's why this active power is also called real power. That is the real power, especially in AC circuits. Okay. So this is graphically how we can show it. This is an average, like from here, the positive half cycle, and this is the negative half cycle. Okay. So this is a kind of example. Before going further, I think it's better to immediately do the example over here, that how to determine instantaneous power, energy, and average power. So these are the waveforms, means the values, actual values, the instantaneous values of voltage signal, or the actual instantaneous voltage, and this is instantaneous current. So we need to find out the instantaneous power just by using these. So we already know Vt multiplied by It is the instantaneous power. For this particular instant, what is the instantaneous power? So this can be shown as an instantaneous power. So at every instant, the power is calculated. So this is a graphical representation. How to do it mathematically? We can do it from here. That we know that from 0 to 10 millisecond, the voltage is 20 volts. 0 to 10 milliseconds, voltage is 20 volts. And from 10 milliseconds to 20 milliseconds, voltage is 0. 10 to 20, it is 0. Again, it is building up the same. So from 0 to 20 milliseconds, we need to calculate the instantaneous power. After 20 milliseconds, it's a kind of a repetition. So we don't bother about this one. So one complete cycle, so 0 to 20 milliseconds. And what about current? 0 to 6 milliseconds, it is 20 amperes. And from 6 milliseconds to 20 milliseconds, 6 milliseconds to 20 milliseconds, it is minus 15 amperes. So instantaneous power is simply Vt multiplied by It. So Vt multiplied by It for 0 to 6 milliseconds, because first we go for 0 to 6, because current is having some value from 0 to 6 and it changes after 6. So for 0 to 6, voltage is 20 volts, current is 20 amperes. So 20 multiplied by 20 is 400 watts. Then from 6 milliseconds to 10 milliseconds, 6 milliseconds to 10 milliseconds, current comes out to be minus 15 amperes and voltage comes out to be again 20 volts. So we can calculate and it comes out to be minus 300 watts. 15 multiplied by 20 minus 15, so minus 300. And 10 to 20 milliseconds, 10 to 20 milliseconds, current is minus 15, but voltage is 0. So V into I is 0. So it is 0. So now what is energy absorbed? Energy is power multiplied by time. So from T1 to T2. So starting from 0 till 20 milliseconds, we have 3 steps: 400 watts, 300 watts, and 0 watt. So 400 watts from 0 to 6 milliseconds, from 6 to 10 milliseconds minus 300 watts, and from 10 milliseconds to 20 milliseconds, it is 0. So this power multiplied by time, and power multiplied by time is energy. So it comes out to be 6 multiplied by 400 is 2.4 milliseconds, or 2.4 joules. And this 10 minus 6 is 4 milliseconds multiplied by 300 is 1.2 joules. 1200 millijoules, it is 1.2 joules. So total energy comes out to be 1.2 joules. So this is an instantaneous power. Every millisecond it is changing, and this is energy. And immediately we can find out the power. One way of doing it is, this is the energy absorbed for complete from 0 to 20 milliseconds. It is 1.2 joules like this, divided by 20 milliseconds, which is the time period, 20 milliseconds, 0 to 20 milliseconds. So it is 60 watts. Another way of finding is like this: 400, 0 to 6 milliseconds, 400. Now we just have to use this equation and then divide by 20 milliseconds, which is the time period, 1 by time period. Huh? And then divide the complete 1.2 joules by 20 milliseconds, we get 60 watts. Either we can calculate this average power like this, or we have already calculated energy in previous case, and directly we divide it by 20 milliseconds, we get 60 watts. So 60 watt is the average power in this circuit. And if we see this instantaneous power, 400 watts, we cannot easily relate to the actual power being consumed by the circuit, because it keeps on changing every fixed time period. It keeps on changing, 400, 300, and then it can be another value. So we do not get an actual picture of the power. So better way is to get average power. Now we can easily say that 60 watt is being consumed by this circuit. Okay. A special case frequently in power electronics is power absorbed or supplied from a DC source. So this is again an average, because we are dividing it by one time cycle. So it is an average value of power. This average value of power is also called DC value of power. So like in rectifier circuits, we get output as DC value. Input is AC, output is DC. So this average output at the DC, average output of rectifier is DC value of the power. So this, for example, in that case, we have calculated what is the actual average value at the output of a rectifier. And that actual average value of power received at the output of a rectifier can also be called as the DC value of a power, because we are actually dealing with the DC at the output of a rectifier. So this average can also be called DC. So the same formula for average can be used for finding out the DC value at the output of a rectifier, let's say. So this is just another way of seeing it. So DC voltage source, we already know that if we are dealing with the periodic values or periodic signals, which can be periodic voltage waveform or periodic current waveform, so we can easily find out the DC value of a power, which is just calculated using the average value of power. So another way of saying it, the average power absorbed by a DC voltage source means if we have a DC voltage source, what's the average power? Or what is the average power received at the rectifier output? We have a VDC, means we get a DC voltage at the output of a rectifier, but the current is calculated using an average, but it keeps on changing. Let's say the current keeps on changing. So we get the average value of current, and still by getting the average value of current, we multiply it with the DC value of the voltage at the output of a rectifier, which can be used as a DC voltage source. We get a DC voltage or DC power. Now another way of saying is we have a constant current at the output, let's say a transistor circuit. So output of a transistor circuit, we have a constant collector current, but the voltage keeps on changing, and we multiply and we changing. So this change in voltage is calculated just by using the average formula like this one. So this voltage over here, we calculate this average value of voltage just by using this formula, Vt multiplied by dt, starting from any instant time t0 to time t0 plus t divided by t, we get V average. So this V average multiplied by the DC current, and we still get the DC value of power. You just have to remember that this DC value of power is just same as the average value of power, but we denote it using DC, that just to show that we are dealing with the DC source, either a DC voltage source or a DC current source. So like DC current source, this transistor circuit. So transistor is also can also be used as a current source. So then this current source, the transistor current source, can have a DC current, and then multiply by the average value of the voltage, we get a DC power. So all these combinations are possible. The only thing is we have to first calculate the average value of that particular signal from the instantaneous value. So first instantaneous value is used to get the average value, and then this average value of that particular signal is multiplied by that DC source, and we get the DC power. Okay, energy storage. So we have already seen what is energy, how to calculate the energy values, what is power, and how to calculate power values. It was just a revision session, quick revision session. Now another quick revision session is that how the energy storage actually happens. So there are two passive elements actually used in power electronics: capacitance, denoted by C, inductance, denoted by L. Using these two components, we can store energy. So we can store electrical energy in capacitor and magnetic energy in inductance. So these two are also called state variables. So this, we need to find out when we analyze the circuit. We already know that for analyzing the circuit, the state of each passive element is actually calculated, whether the capacitor is charged or not. So means there are two states of this state variable called capacitor. One is charged state, another one is discharged state. And for inductance also the same thing. Again, state variable, it has two states. One is charged state or fully energized state or de-energized state. So this capacitor gets charged when a voltage is connected across it. And then this charge starts to being developed inside the capacitor, and once it is fully charged, we say that the state is changed now from uncharged to charged. For inductor also, initially it is uncharged, it acts as an open circuit, and then the current starts to build up inside the inductance, and then energy is stored in terms of magnetic energy in this coil, which is inductance. So we have a full energy stored in inductance. So these two states in capacitor and inductor play an important role in any electrical circuit. So again, periodic signals we are dealing with, and we know this IT current means that particular instant current at particular instant t is same as current in that particular instant plus one complete time period, because periodic in nature. The same happens for voltage. And energy stored in inductance is half Li square T. And we already know V is L di by dt. The rate of change of current in that particular inductance will give us the EMF, the voltage. Multiply by current, we get half Li square, which is energy. Multiply by time, which is T. So we get energy. So that is the total energy stored in that particular inductor. So in one particular time instant, let's say for sinusoidal, we have one positive half cycle and one negative half cycle. In positive half cycle, the energy gets stored in inductor, and in the negative half cycle, the energy gets used by the circuit from that inductor. And we'll be using this technology or this one storage of energy in our power converter circuits. So in that case, what we now can say is no net energy transfer indicates that the average power absorbed by an inductor is zero. So in one half cycle it stores, and in negative half cycle it throws away or it gives up the energy. So we can say that average it is zero. Whatever is stored is thrown out in the next half cycle, and in the complete one cycle there is net is zero. Again, instantaneous power for inductive circuits. For periodic, we know this, and this voltage starting from time t0 to the complete one cycle, this is the voltage across inductor, multiplied by time. Voltage multiplied by time in that inductance divided by L is the current. So, and we whatever voltage gets across the inductor divided by that particular value of inductor, and we keep on integrating it for complete time cycle, we get the current for that complete one cycle. And then rearranging the equation 10, taking this, the initial value over here, and we get this value and equating it to 0, because we already know the net is 0. Whatever is stored is thrown out. So for periodic signals, the net value is 0. So we equated to 0, and then multiplying by L by T, multiplying this by L by T, we get 1 by T, VL T dt is 0. So the average value of this is 0. The average value of voltage across the inductor is 0. Again the same thing, because whatever comes in goes out. So we need to just use these values. From these values, we multiply L by T. Capacitor also the same thing. We already know the value of current in capacitor is C multiplied by rate of change of voltage. So the voltage keeps on developing and the charge keeps on building up in the capacitor, and we get the current. And the change in voltage is equal to, because we rearrange this value, this equation, we get this. So impedance decreases with frequency. So impedance in this case is XC, the capacitive reactance. And the capacitive reactance, we know it decreases with frequency for capacitor. And stored energy is actually equal to square of the voltage, CV square. Again, using that formula, so this is the voltage, this is the current. Current multiplied by voltage multiplied by time, we get this half CV square multiplied by time. So this energy stored is actually proportional to the square of a voltage. So the stored energy, again, the thing is the net value is 0. Whatever goes in, whatever is stored, it goes out. Whatever is charged, it gets discharged. Again, the net value is 0. Using again the same thing, voltage at this instant, initial instant is VT0, initial value, initial condition, and the voltage from that initial condition to the one complete cycle is VT0 plus T, which is equal to this 1 over C integral T0 to T0 plus T, this one, starting from initial to the final value, the capacitor current multiplied by the time. Okay, so this equation we already know from here and from here. Rearranging this final value minus the initial value, we get this, equating it to 0 because the net value is 0, and then multiplying it by C by T, we get average value of current. So the average value of a current in a capacitor is 0. For periodic, because in power electronics we are talking about sinusoidal signals or square wave signals later on. So all these are periodic in nature. So in that case, the net value is 0. So these things we will be using when we do our power converter circuits. So you have to remember these formulas and these conditions. So conditions written in red or in bold, you have to remember when, because these we'll be using in power converters. Okay, again another example, just how the energy gets stored and then released. One example I'm describing over here, and the next example you have to do at home. A circuit would energize an inductance and then transfer the stored energy to a resistor. Same thing, which we have done earlier mathematically. Now using circuit, how to say that, okay, it actually happens. This is the actual circuit, a transistor triggered with these pulses. And we have a diode here, a resistor, and this is an inductor. So diode acts as a switch and a transistor acts as a switch. Now, active switch, transistor is on. In first instance, the transistor is on. And then in the next instance, the transistor is off. So just in first condition, when transistor is on, how it happens? First condition, when transistor is on, the voltage across the inductor is VL equal to VCC. Because when the transistor is on, this diode, when the transistor is on, the current starts to flow like this. I will show it from here. When the transistor, the current flows like this because the circuit is completed now. So the current from this power supply VCC flows through the inductor into a transistor and then to the ground. And from here, this collector is connected to an inductor and emitter is connected to the ground. So common emitter configuration. You have already studied in basic electronics. So this collector current now is equal to the inductor current. And this complete voltage over here, because this inductor, it is initially open circuit, de-energized. So the complete voltage over here in the collector voltage, CC supply voltage, is applied across the inductor. And then the current slowly starts to build up. And this diode is reverse biased when the transistor is on. So the current starts to flow and this diode is turned off because of this initial, when the voltage, complete voltage is applied. What happens when the transistor is off? When the transistor is off, when the transistor gets off, due to the stored energy inside the inductor, which was stored when in the previous cycle, due to the switching on of the transistor, the energy slowly gets built up in the inductor, and the current flowing in the inductor is same as the current from the supply. Now in this case, the current keeps on flowing, switch is off. So now current will not go or follow this path. Current will follow this path and the diode gets on or reverse forward biased. And then this forward biased diode will close the switch and the current will keep on flowing like this. So the current IL will keep on flowing as long as the stored energy inside the inductor is fully de-energized. So this is how the waveforms look like. Initially, the inductor current slowly builds up like this, reaches maximum value when the transistor is on. Now here the transistor gets off and the stored energy is being used to flow the current in the resistance. So the current starts to slow down and it reaches to zero over here. Again, when the transistor gets on, the inductor current starts to build up till it reaches maximum value. So the inductor is fully energized here. And when the transistor gets off, when it is turned off, when the transistor is turned off, the inductor current starts to go to zero and the inductor starts to get de-energized, and here it reaches zero value. This is how the inductor actually works, and we get a useful work done by the inductor. So only for a few seconds the transistor gets on, and then we can just turn off the transistor and the actual work is now done by the inductor. And we have smooth current flowing like this. And these ripples can be modified or removed by having filter circuits and all these things. That will be a separate part. But this is just to show you that how inductor is useful in electronic circuits or power electronic circuits. This you have to do at home. In this case, we have 2 transistors instead of 1 and 2 diodes instead of 1. That's the only difference. But actual concept is same. When transistor is on, how the current or how the inductor is energized, and when the transistor is off, how this energized or stored energy in the inductor is actually used by the circuit. This is actually detailed over here. So you can do your homework and then we'll see. So this discontinuous current means when the current becomes zero, it keeps on zero for some time. And again, it builds up. This is called discontinuous current. We will be doing this in our power converters section. Again, a revision of Fourier series, which you have already done in your mathematics syllabus, linear algebra and mathematical techniques. So Fourier series. Fourier series is actually used in power electronics to analyze these circuits for doing harmonic analysis. So we can say that when and why we go for Fourier series. Normally, when the switch action is periodic by design, and we already know that power electronics, we deal with the periodic signals. So in that case, we can say that a switching action or the switching of the devices is also periodic in nature. So specific input frequencies, and we want specific output frequencies, but instead of specific or specified input frequencies and the targeted output frequencies, we actually have other frequencies inside our voltage and current and power signals, which may not be required. So we may need to get rid of all these other types of frequencies or unwanted frequencies. So it means we need to explore the frequency content of our waveform. And you already know that Fourier series deals with the frequency components of a signal. So let's say this is a kind of a periodic signal, a distorted sine wave. Not the real sine wave, but distorted. But still periodic, because it keeps on repeating itself. So before going further, I must say that, okay, this is a distorted sinusoidal signal, periodic in nature, but we want a clean sinusoidal signal. So it means it has the frequencies which we actually want, but at the same time, these required or actually wanted frequencies are superimposed by some unwanted frequency signals. And we want to get rid of all these frequency signals so that we get a clean sinusoid. So that's the whole idea behind using Fourier series to do harmonic analysis. And once harmonic analysis is done, we can use filters to remove all the unwanted harmonics, to remove the distortion. So this signal Ft, which was this one, this, can easily be represented like this. This is the fundamental component, and these are the cosine components and sinusoidal components. So we can, using Fourier series, we can decompose the Ft, which was shown previous slide. We can decompose, or we can break this signal into set of sinusoidal and cosinusoidal signals, components. And we know that this can be possible using Fourier series. So this fundamental can be calculated by integrating the actual function from any time instant t0 to t0 plus 1 time cycle, and then taking an average divided by 2. Okay, and then this coefficient an, this is a fundamental, this is coefficient fundamental component, this coefficient an is calculated by this Ft superimposed with cos omega t. So this cos omega t multiplied by some frequency components, nature of, so this is our fundamental component, fundamental frequency component, and has a multiple with n can be 1, 2, and so on. So means the first fundamental component, second, third, and so on. So this value will have, if n is equal to, let's say, 2. So this component A, so n is equal to 2. So A2, coefficient of A2 is having twice the frequency of the fundamental component. So that is called the second harmonic. If n is equal to 3, So the frequency is now 3 times of the fundamental component. So that is called the third harmonic, which is A3. So this is the third coefficient. Another coefficient is sinusoidal coefficient. In the next slides, we'll see that. So now, as seen in the previous slide, the cosine components and the sine components, or sine coefficients or cosine coefficients. So AN are cosine coefficients, which are called even coefficients, and these are the odd coefficients. So this is the fundamental part, the DC part, 0. Odd part is 1, 3, 5, 7, and so on. Even part is 2, 4, 6, and so on. This is 2 pi n. N can be the value of that coefficient multiplied by t divided by 1 time period t. And this is the fundamental frequency, 2 pi by t is the time period. So then multiply this fundamental frequency with a factor n can give us that multiple frequency component, which is called multiple harmonic. So we can represent this ft in 2 pi n t by t or n omega by multiplied by t. Both are the same thing. So because we already know 2 pi by t is omega naught. Okay, to go further. So now this one, n omega naught, is called the nth harmonic. So if n is, let's say, 5, so it is the 5th harmonic. If n is 7, this is 7th harmonic, and so on. So we have to deal with odd and even harmonics separately. Okay, so from the previous slide, we can say that this we can multiply this with a square plus b square divided by a square plus b square. Just divide with the root. We get the same value over here. And once we do that, just divide and multiply with this one, the complete one, we get this value. An divided by an square plus bn square, it is cos theta n. This is also sin theta n. Now, this value over here, if we simplify this equation, we get this value, this one, where Cn gives us the value of, the amplitude of that particular harmonic, and theta gives us the phase angle of that particular harmonic. And C0 is just this K0 by 2 is denoted by C0. So this is one form of calculating the harmonics, this one. And if we just simplify it by multiplying and dividing by this value, we get a simplified version in this form. This form will give us different harmonics and different n values. This will give us this is kind of a polar form. So we have converted this form into a polar form, which gives us the amplitude of that particular harmonic, depending upon the value of n over here. So the amplitude of that particular harmonic and the phase of that particular harmonic. This actually gives us the actual value. So this is one way of representing the harmonics, and this is another way of representing an harmonic. So in this way, we can just say Cn gives us the amplitude of that particular harmonic or coefficient, and this theta n gives us the phase angle. And this theta n is calculated by tangent inverse of Bn by An. And Bn we already know is this, sinusoidal divided by the cosine. Bn divided by An, and taking inverse of tangent we get the theta n. And An square by Bn square is simply Cn, which we saw in our previous slide. So this is one way of representing the signal in terms of harmonics, simple harmonic amplitude and the angle, a polar form. So this is now the function. So it means this function ft has been now represented by this, or more simpler way, it has been represented by this, that particular waveform. A distorted sinusoidal waveform has been represented by this value. So for every n value, we have different Cn and different theta n. Omega n will be different, of course, but different theta n and different Cn. So easy to calculate using these values. Example we'll do later in the next class. We'll do example because now the time is over. So next class we will do that.